and welcome to Earth SciShow, the podcast where we explore the fascinating mysteries of our planet. I'm your host, MrEarthGuy, and today we're going to talk about a groundbreaking discovery that could reveal secrets of the Earth's history and evolution. You've probably heard of the Earth's core, that giant ball of metal at the center of our planet that generates our magnetic field and keeps us safe from cosmic radiation. The core is separated into two parts, an inner core and an outer core. And did you know that the inner core itself might have another layer inside? We call this the innermost inner core. Very original, I know. Us geologists like to keep things simple. In some groundbreaking research, scientists have recently found evidence of a mysterious ball hidden within the inner core. And they seem to have stumbled across this by using a brand new technique which involves listening to the echoes of earthquakes. Sounds pretty cool, right? Well, stick around because we're going to dive deep into this discovery and understand what it means for the Earth's formation and its evolution over time. But before we do that, please remember to drop us a follow and hit that notification icon. If possible, leave us a review on your favorite podcast platform and share this episode with your friends who love science as much as you do. It really helps us grow our audience and keep this show going. Thank you so much for your support. Let's get to it. So how do we know anything about the Earth's core in the first place? We can't exactly drill down there and take a look because it's way too hot and dense for any human-made device to survive. The core is located around 6,400 kilometers below the surface and has a temperature of around 5,000 degrees Celsius. It has a pressure of about 3 million times that of our atmosphere. That's like being squeezed by an elephant while standing on the sun. So instead of drilling, we use seismology, which is the study of seismic waves. These are vibrations that travel through the Earth when there's an earthquake or an explosion. By measuring how these waves change speed and direction as they pass through different layers of the Earth, we can infer what those layers are made of and how they behave. For example, we know that the outer core is liquid because seismic waves that can only travel through solids, called S waves, can't go through it, while seismic waves that can travel through both solids and liquids, also known as P waves, can go through it but slow down significantly. We also know that the inner core is solid, mainly because P waves speed up again as they enter it. We can also detect the reflections of the P waves as they move from the outer core to the inner core. It's worth noting that seismology does have its limitations. It's not easy to get good data from the inner core, especially its center, because we need earthquakes and seismometers that are very close to each other on opposite sides of the planet. We call this antipodal. And even then, there are many factors that can affect the seismic waves, such as variations in temperature, pressure, composition, and structure in the mantle and core. That's why scientists have been looking for new ways to probe the inner core and reveal its secrets. And one of these ways is by using reverberating waves. So what are reverberating waves? Well, these are seismic waves that bounce back and forth between two boundaries multiple times before they reach a seismometer. For example, if an earthquake happens near one side of the planet, some of the P waves will go through the outer core and then reflect off the inner core and repeat this process numerous times before the waves eventually reach the other side of the planet and are picked up by the seismometers. These are called PKIKP waves. Don't worry about what that stands for. From now on, we'll call them PKIP waves. And they can be detected as very faint signals after the main P wave arrives at the seismometers on the other side of the planet. So we've discussed reverberating waves going from the outer core to the inner core and back to the outer core again. But now imagine those PKIP waves going through the outer core and then staying within the inner core and reverberating inside that layer. These are called PKIP multiples. So how are PKIP multiples used to study the inner core? Well, PKIP multiples are very rare and hard to observe because they require very specific conditions of earthquake location, seismometer location, and wave frequency. But thanks to the growing number of global seismic stations and advanced data processing techniques, scientists have recently been able to detect them for the first time. By stacking waveforms from multiple earthquakes and seismometers, they were able to enhance the weak but coherent signals of the PKIP multiples and identify them as distinct arrivals on the seismograms. Think of stacking as putting many sounds that sound the same together to amplify their volume. And by using this process, they observed up to 5-fold reverberations, meaning that some P waves went through the entire Earth's diameter 5 times before reaching a seismometer. That's like going around the world 10 times in less than an hour. By measuring the travel times of these exotic waves and comparing them to the theoretical predictions, they were able to infer how fast P waves travel in different directions in the inner core. And what they found was surprising. P waves travel at different speeds depending on the angle relative to the Earth's rotation axis. This means that the Earth's inner core is anisotropic, or it has different properties along different directions. But that's not all. They also found that this anisotropy changes with depth. In the outer part of the inner core, P waves are faster along the polar direction and slower along the equatorial plane, while in the innermost part of the inner core, P waves are faster along both the polar and the equatorial directions and slower at the mid-range latitudes. This suggests that there is a transition zone between these two regions. This is where the anisotropy flips. Okay, great. We found out that there is anisotropy in the Earth's inner core. But what does this mean for our understanding of Earth's history and evolution? This discovery has important implications for our understanding of how the inner core formed and evolved over time. The inner core is believed to be a time capsule of Earth's history because it grows slowly by freezing from the liquid outer core over billions of years. As it grows, it releases heat and light elements that drive the convection currents of the outer core and power the geodynamo. This helps generate the magnetic field. The anisotropy of the inner core reflects how iron crystals are aligned in its solid structure, which depends on factors such as temperature, pressure, composition, and magnetic field. By studying how this anisotropy varies with direction and depth, we can learn more about how these factors changed over time and what events might have influenced them. For example, some scientists think that the anisotropy in the outer part of the inner core is caused by thermal convection or preferential crystallization that aligns iron crystals along the Earth's rotation axis. But others think that it's caused by sedimentation of light elements at the boundary between the inner and outer core, which creates chemical variations in both layers. The anisotropy in the innermost part of the inner core is even more puzzling. Some scientists think that it's caused by a different crystal structure of iron that stabilizes at higher temperature and pressure conditions, but others think that it's caused by a change in the deformation pattern or magnetic field orientation that reorients iron crystals at some point in Earth's history. The exact causes and mechanisms of these anisotropic patterns are still debated and require further investigation. But one thing is clear. They indicate that something significant happened in Earth's past that left a fossilized record in its center. And by using these new techniques like K-pip multiples, we might be able to decode this record and reveal more secrets about our planet. As with most things in science, the answers are still yet to come. And that's it for today's episode of Earth SciShow. I hope you enjoyed learning about this amazing discovery and how it helps us understand our planet better. And if you like this episode, please don't forget to follow us on this platform, leave us a review, and share this episode with your friends. Until next time, stay curious and keep exploring.